Welcome to G Fun Facts Online. Humanity's dream of reaching Mars is closer than ever, but between us and the red planet lies a vast, unforgiving void. And in that void, the most immediate challenge isn't radiation or food, it's the simple, constant act of breathing. For a multi-year journey, a life support failure isn't an inconvenience, it's the end of the mission. The systems keeping astronauts alive on the International Space Station, just 250 miles away, are brilliant, but they are fundamentally wrong for deep space. They are heavy, power-hungry, and prone to breaking down. So how do we solve this oxygen conundrum? The answer isn't a more complex machine, it's a force of nature, magnetism. By harnessing a strange quantum property of oxygen itself, we may be on the verge of a revolution in life support, one that could finally make deep space travel a sustainable reality. To understand this leap, we first need to look at the fragility of our current systems. On the ISS, oxygen is made through a process you might remember from chemistry class: water electrolysis. Electricity splits water, HO, into hydrogen and oxygen gas. On Earth, the gas bubbles are less dense than the water, so they float to the top to be collected. Simple. But in the microgravity of space, there is no up. The bubbles don't float. They stubbornly cling to the electrodes where they're made, forming an insulating blanket that chokes the reaction and kills its efficiency. The ISS solves this with brute force, a centrifuge. A component called the rotary separator accumulator spins rapidly, creating artificial gravity to force the gas out of the water. It works, but it's a perfect example of engineering that is completely unsuited for a trip to Mars. This reliance on high-speed rotating machinery introduces countless points of failure. Pumps, motors, bearings, they all wear out. The ISS life support system has faced a constant stream of problems, from pump failures to sensor glitches. The maintenance is relentless. Studies show that astronauts can spend between 13 and 15 hours per week just keeping the life support system running. That's nearly 2 full workdays spent on maintenance. This is manageable when you're in low Earth orbit, with ground control on the line and regular resupply missions bringing spare parts. But on a Mars mission, the crew is utterly alone. There are no spare parts coming. A NASA report stated in no uncertain terms that the current ISS oxygen system is simply not feasible for a Mars transit mission. Beyond reliability, there's the issue of resources. The ISS oxygen generator consumes over 3,500 watts of power. That's a huge drain on a deep space vessel where every watt is precious. And the system is heavy. The centrifuge, pumps, and plumbing all add mass, and launching mass into deep space is astronomically expensive. The challenge is clear. We need to reinvent how we make our air. The solution starts not with engineering, but with a surprising quirk of quantum mechanics. We don't think of the air we breathe as magnetic, but molecular oxygen, O, is what's known as paramagnetic. This means it's weakly attracted to magnetic fields. This property, often just a neat classroom demo where liquid oxygen is suspended between magnets, is the key to a new generation of life support. The reason for this magnetism lies deep in oxygen's electron structure. A concept called molecular orbital theory correctly predicted that an O molecule has 2 unpaired electrons spinning in the same direction. This gives the molecule a tiny magnetic moment, making it behave like a microscopic magnet. In contrast, water and hydrogen gas are diamagnetic. All their electrons are paired up, so when exposed to a magnetic field, they are faintly repelled. On Earth, these forces are so feeble, they're completely swamped by gravity. But in microgravity, they suddenly become powerful enough to command. The real trick happens when you use a magnetic field gradient, a field that changes in strength from one spot to another. In this kind of field, paramagnetic oxygen is actively pulled toward the strongest part of the field, while diamagnetic water is actively pushed toward the weakest part. This is the core principle. In 0G, where bubbles have no reason to go anywhere, a magnetic field can provide the force needed for separation. It creates an artificial, magnetically induced buoyancy, pulling oxygen bubbles off the electrodes and away from the water, all without a single moving part. An international team of researchers, including Dr. Alvaro Romero Calvo at Georgia Tech and Dr. Katharina Brinkert at Germany's ZARM Center, are turning this physics into technology with funding from the NASA Innovative Advanced Concepts program. Their project is called MOGA, the Magnetohydrodynamic Oxygen Generation Assembly. They're exploring two main techniques. The first is passive magnetic separation. This is the most direct approach. By placing powerful neodymium magnets right next to the electrodes in an electrolysis cell, they create a strong magnetic gradient. As an oxygen bubble forms, its paramagnetic nature pulls it toward the magnet. At the same time, the diamagnetic water is pushed away. This gentle push and pull is enough to detach the bubble and guide it to a collection port. It's entirely passive, requiring no extra power and no moving parts. The second, more active method uses magnetohydrodynamics, or MHD. This principle describes how magnetic fields interact with electrically conducting fluids, like the electrolyte-infused water in an electrolyzer. By applying a magnetic field perpendicular to the electric current that's already running through the water, a Lorentz force is generated. This force causes the water itself to swirl into a vortex. This induced flow creates a centripetal force that acts just like a mechanical centrifuge, flinging the denser water to the outside and driving the less dense gas bubbles to the low-pressure center of the vortex for easy collection. It is, in essence, a centrifuge with no moving parts. To prove these ideas work, the teams have used the ZARM Bremen drop tower in Germany. This 146-meter tower allows a capsule to fall for 9.2 seconds, creating a perfect microgravity environment. Inside this falling capsule, experiments have shown unequivocally that magnets can manage the gas bubbles. High-speed video shows oxygen bubbles streaming cleanly away from the electrodes when the magnet is on, while in control tests, the bubbles remain stuck. The results are spectacular. The data shows that applying these magnetic forces can bring the electrolysis process back to near-Earth levels of performance. In some cases, the efficiency of the electrochemical cells was boosted by an incredible 240%. These tests are concrete proof that magnetic separation is a viable, powerful solution. The advantages of this technology for deep space travel are profound. First and foremost is reliability. By eliminating all the moving parts, the pumps, the motors, the centrifuges, you eliminate the primary sources of wear, leakage, and failure. A solid-state system is just inherently more robust. The NASA project summary from MOGA estimates this could lead to a 20.4% reduction in the time astronauts spend on maintenance. That's a huge win on a long mission. Next are mass and volume savings. Every kilogram launched to Mars costs a fortune. By replacing the heavy centrifuge and its plumbing, the magnetic system is projected to reduce the oxygen generator's mass by 32% to 50%. This is an enormous saving that directly impacts the cost and capability of the entire mission. Then there's performance. As the drop tower experiments showed, magnetic separation isn't just a replacement, it's an upgrade. By efficiently clearing the bubbles, the system boosts the oxygen production rate for a given amount of power. An efficiency gain of 240% means more oxygen from less energy, a critical factor on a power-constrained spacecraft. Finally, the system is gravity independent. The magnetic forces are the same, whether you're in 0G during transit, the 1/6 gravity of the Moon, or the 1/3 gravity of Mars. This makes it a universal solution for a mission that may operate in multiple gravitational environments. Of course, the path from a 9-second experiment to a human-rated system that can run for 3 years is long. Researchers must solve the challenge of scale. What works in a small lab setup might behave differently in a large system needed to support a full crew. The technology needs longer duration tests on suborbital flights and eventually on the ISS. There's also the question of the magnets themselves. While permanent magnets require no power, some designs might need stronger fields from superconducting electromagnets. These require heavy, complex cryogenic cooling systems, which add their own mass, power draw, and failure points. And strong magnetic fields on a spacecraft are a hazard. We need more research on the long-term health effects for the crew. Stray fields could also interfere with sensitive science instruments and navigation equipment, requiring heavy magnetic shielding. But the potential of magnetic fluid management extends even beyond the cabin air. It's important here to distinguish between MOGA, the life support system, and another famous oxygen experiment, MOXIE. MOXIE, which flew on the Perseverance rover, was a groundbreaking demonstration of in situ resource utilization, or living off the land. It proved you could make oxygen on Mars by extracting it from the planet's carbon dioxide atmosphere. MOXIE's goal was to produce oxygen not for breathing, but as a component of rocket propellant for the return journey. A future, scaled-up MOXIE would be a chemical plant on Mars, producing tons of liquid oxygen to fuel the Mars ascent vehicle. So MOGA and MOXIE are two sides of the same coin. MOGA is the closed-loop recycling system for breathing on the way to Mars. MOXIE is the open-loop production plant for making fuel to get home. The same physics can also solve another major problem: managing cryogenic propellants like liquid oxygen and liquid hydrogen in zero-G. In a fuel tank without gravity, the liquid doesn't stay settled at the bottom. It can slosh around, creating a frothy mix of gas and liquid that can choke an engine. But since liquid oxygen is paramagnetic, magnets could be used to hold it securely over the fuel pump intake. For diamagnetic liquid hydrogen, magnets could be used to push it into place. This would make cryogenic propulsion systems, essential for deep spaceflight, far more reliable. The journey to Mars will push humanity to its absolute limits. The crew on that mission will need to have total faith in the systems providing their every breath. The mechanical life support we use today, while a marvel for near-Earth orbit, is simply too fragile for the journey into deep space. Magnetic oxygen generation represents a fundamental shift in thinking. It moves away from complex mechanics and towards an elegant, solid-state solution that is more reliable, more efficient, and better suited for the harsh realities of space. By harnessing a quantum property of the very air we breathe, we are developing a system that is perfectly tuned to the microgravity environment it must conquer. While challenges remain, the promise is undeniable. A life support system with no moving parts, a system that is lighter, more efficient, and far more reliable than anything we have today. As we look towards the red plains of Mars, it may be the silent, steady force of a magnet that ensures we can breathe easy all the way.